Warahmatullahi wabarakatuh. Good morning. In previous lecture, we have discussed that the partition function of an assembly can be obtained from the partition function of one particle in a very simple mathematical equation, that the partition function of an assembly is the power n of the partition function of one particle. So, based on this approach, we can simplify the calculation. We don't need to directly calculating the partition function of an assembly. We can use a more simple procedure by calculating the partition function of one particles, and then from that partition function, we can develop the partition function of an assembly by the power of n of the partition function of one particles. Now we will show one example how to use that approach, and we'll also demonstrate that both approaches will end at some conclusions. Now we will consider again the example we have discussed in the previous lecture, that an assembly contains n magnetic moments, and in the assembly we apply a magnetic field to reorient the direction of the magnetic moment is the assembly. Now let us consider again the assembly we have. We have n magnetic moment. Without the application of the magnetic field, the direction of the magnetic moment in this assembly is random. All direction will be had by the magnetic moment, so the total magnetic moment is 0, because all direction can be found in this assembly. If we sum all of the magnetic moment, the total is 0. Now, if we apply the magnetic field in this assembly, suppose in the direction of vertical upward, then the magnetic moment inside the assembly will adjust the direction so that large fraction of most of the magnetic moment will direct parallel to the magnetic field, and then small amount will direct opposite to the magnetic field. We have calculated the magnetic moment. If the magnetic moment is in the same direction, with the magnetic field, the energy E1 epsilon 1 is minus mu B. Mu is the magnitude of the magnetic moment and B is the magnetic field. Now for the opposite magnetic moment, we will have the energy is epsilon 2 plus minus mu, plus mu multiplied by magnetic field. So the energy of magnetic moment that parallel to the magnetic field is smaller than the magnetic moment having opposite direction to the magnetic field. Now we have discussed previously that if the number of magnetic moment that parallel to the magnetic field is n, small n is the number of magnetic moment that parallel to the magnetic field, and n plus n minus small n is the number of magnetic moment. magnetic moment that opposite to the magnetic field, then the total energy of assembly in these configurations, the assembly energy will be E, n is the number of magnetic moment in the same direction with the magnetic field, and large N is the total number of magnetic moment, is 2 times n small n minus large N and mu b. This is the assembly energy when n magnetic moment is in the same direction with the magnetic field, and n large N minus small n is the number of magnetic moment in opposite direction. So the energy of the assembly is 2n small n minus large N times mu b. But the assembly can have any value of small n from 0, 1, and up to n. So we will have a large number of possibility for the assembly to have the energy, the total energy. Now, in calculating the partition function, we have to accommodate all the possibility in the summation to determine the partition function. We have also discussed that for any choice, any small n, there are a large number of configurations. For one small n, we have a large number of configuration, but keep the energy still constant. So for one energy, we have a large number of configurations. So in calculating the partition function, all configuration must be accommodated in the summation. The number of configuration when n magnetic moment is in the same direction with the magnetic field, we have discussed this is equal to number of configuration is n large N divided by small n factorial and large minus small n factorial. So the partition function for this assembly partition function for this assembly becomes Z equals to summation n large N, small n, and minus small n, exponent minus a n comma n press kt. So to determine the partition function of the assembly, we have to solve this summation, where this is the 2n small minus large n mu b. This calculation needs some mathematical effort. For example, we have to approximate the factorial with the Stirling function. This is approximated with the Stirling function, and then we apply in the summation to determine the partition function. In previous discussion, we have demonstrated that to avoid this difficulty, we can start from the partition function of single particle. We don't need to calculate directly the partition function of the assembly, but we just need to calculate the partition function of one particle, and from that partition function, we'll calculate the partition function of the assembly. Now we will try. Because the particle have two possibility of energy, the possible energy of particles is epsilon 1 minus mu b and epsilon 2 plus mu b. Because the particle only have two possible energy, then the partition function of the particle contains only two terms. One is contributed by epsilon 1 and one is contributed by epsilon 2. So, the partition function of particles is just small z equals to epsilon minus A1 divided by KT plus epsilon exponent epsilon 2 divided by KT. This is the simple equation. We only account two terms from epsilon 1 and epsilon 2 because particles have only two possibility of energy. That's different from the assembly. Assembly have a large number of possibility. For one energy, we have a large number of possibility, and the small n can vary from 0 to n. Then the terms in this summation is very large. But in case of particle, we have only two terms. From one contributed by epsilon 1 and second contributed by epsilon 2. If we put this value, we will have exponent mu b divided by kt plus exponent negative mu b divided by kt. This is the partition function of particles, one particle. Now, from this partition function, we calculate the partition function of the assembly by simple equation as we have discussed in previous lecture. So, the partition function of assembly becomes large z equals to small z power n equal to exponent mu b divided by kt plus exponent negative mu b divided by kt power n. This is the partition function of the assembly, and the calculation is very simple. Now, from these two possible energies, we calculate the partition function of one particles, and we obtain a simple equation, and then we calculate the partition function of assembly, and we just do a very simple steps. Now, from this partition function, we are ready to determine the energy of the assembly from the definition we have derived in last lecture. Energy of the assembly using a simple equation kt square d partial dt from large z. Now we can calculate simply. This is equal to n kt partial derivation against t, and this is exponent epsilon natural logarithmic exponent plus mu b divided by kt plus exponent minus mu b divided by kt. Now we calculate this equation. It becomes the assembly energy nkt square, and then this is divided equals to 1 exponent mu b per divided by kt, exponent negative mu b divided by kt, and then per partial derivation against t, exponent minus plus mu b divided by kt plus exponent minus mu b divided by kt. And if we calculate this, we have nkt squared. This is the same, mu b divided by kt minus mu b divided by kt. And we derive this one, we will obtain exponent mu b divided by kt. This is negative mu b divided by kt squared. And this one square, and then plus exponent minus mu b divided by kt, and this is plus mu b divided by kt square. And if we calculate it, solve this one, we obtain kt square. Kt square will disappear, and negative and mu b exponent mu b divided by kt minus exponent mu b divided by kt, exponent minus mu b divided by kt plus exponent, this is minus mu b divided by kt. And we finally obtain that the energy of the assembly becomes min 9 minus n mu b hyperbolicus of tangents mu b per kt. This is exactly the same as the equation we derived by calculating the partition function of the assembly first, and then use the same derivation, we obtain this equation too. So we have proof now that we can determine the partition function of the assembly by calculating first the partition function of particles, and then from the partition function of the particle, partition function of the assembly is just a power of n of the partition function of the particles. And we demonstrated here that the energy of assembly calculated by both approaches are exactly the same. So from now we can use this method to avoid the difficulties in calculating the partition function of the assembly. Now we will show another example in the next lecture, how this method, to demonstrate that this method is very powerful in solving many problems in statistical mechanics. So we can solve the problem that we cannot be solved directly using the partition function of the assembly can be solved easily using this approach by first calculating the partition function of particle. As the assembly is considered only contains one particle, we calculate the partition function of assembly containing only one particle, and from that result we then calculate the partition function of the complete assembly by powering with n is the number of particles, and from the partition function we ready to derive all of the macroscopic quantities in thermodynamics. Now I will stop this lecture now, and we will continue later.